Hey there, welcome back. Today I'm going to be teaching y'all about derivatives. Today is our intro to derivatives, how they work, what they actually are, and I don't know, just how to think about it. I'm expecting that y'all have already learned about limits because limits are incredibly crucial to this. I'm not going to be covering limits because I just didn't, so you're going to have to deal with that. Anyways, what is a derivative? Well, first, we're just going to start talking about some examples, well, before I start getting to some really complex theory. So, a derivative is essentially a limit at a specific point. So when you learn about limits, you probably learned about limits when they approach places that aren't defined. Like, oh, we have an asymptote. What's the limit as you approach that asymptote? Or you could have a hole. Be like, what's actually the value at that hole, or that stuff. But derivatives come from the part where you have a limit as you approach a specific point that actually is defined. Your teacher might have mentioned, like mine did, oh, that's not necessarily a limit that we care about for now, when he was teaching you about just the basic theory of limits. He was like, oh, it's just a full limit. We don't need to worry about it. It would have looked something like this. So, say like x equals 5, and it would have been like, what's lim as x approaches 5? Like, evaluate that. This, in like the most basic sense, is essentially our derivative, or the start of the theory of our derivative. You see, the derivative, I'm going to state it simply now, is the rate at which you are changing. So it's the rate of change. So let's think about cars for a second. Say you have a car, or you're in a car, and you're driving along, or you're going from point A to point B, I don't know, from your house to school. And while you're moving, you could consider your situation as a function of time. So after 10 minutes, oh, I've gone 3 miles. After 20 minutes, oh, I've gone 8 miles. After a given amount of time, you've gone this distance. Now, while you're driving along the road, you're just kind of hanging out. You're not exactly going the same speed the entire time, right? Well, while you're going, you look down your speedometer and it says 30 miles an hour. That speed is the rate at which your position is changing. Let's put on a graph. You see that okay? Okay. So we have x, which is time. See that? Perfect. And then y, which is your distance. Distance. Okay. You see that? Okay. Yeah, you can. Okay, so you can look at your graph and be like, oh, I want to know how far I've gone after this amount of time. Let's say after, I don't know, if x is in terms of minutes, after 10 minutes, and let's say this is 10. You come up here and you're like, oh my gosh, I've gone 30 whatever, 30 feet, 30 miles, whatever it is. Like, oh my gosh, that's how far I've gone. This is the basic use of a graph. Pretty nice, and you can tell where it is. But how fast are you going at that specific point in time? Well, what's the distance formula? Or the velocity formula? We're going to go back to physics. Velocity equals distance over time, which is equal to change in y over change in x. Now, this is the slope. That's going to be your speed. If it's constant, this would essentially be this, like boom, that would be our average rate of change. And we could use that as like a constant to go throughout it. However, well, I'm not going to go into the however first. So when you get the concepts down, that we use our two variables and we derive or extrapolate our speed based on that. Now, this, even though this is technically our velocity, which we've extrapolated from a graph, this is not yet the derivative. Another word for derivative is the instantaneous rate of change. So see, this is the average rate of change because it's the change in y and the change in x. Like if we're from here, which is A, and this is B, physics would be like, oh yeah, if this is 10 and this is 30, then you were moving at 3 miles an hour. But you can see that our speed was actually kind of different. We went like faster right here, and then we're kind of going slower. And in the end, we could math it out to be like, oh yeah, 3 miles an hour on average. But at this point, it looks more like we're going like 6 or 7 miles an hour. Over here, it looks like we're actually going backwards for a second. Uh, -2 miles an hour, who knows? So we want to know, what is our speed at a specific point? Like, how fast was I going right there? Like, specifically at that point. I can't exactly have an A and then a B and say, oh yeah, because then that's an average. So I want you to get this into your head. Average rate of change, average rate of change, and instantaneous or instant rate of change. And so derivative is just that. What is our rate of change at a specific point in time with no regards to change over time, just a specific point in time? Now, that might seem confusing to you. Like, how can I know how fast I'm going if I have no point A to point B to compare between? Well, that's actually how we get into the beginning, was my there it is. The beginning of the theory of derivatives. You see, you can take the average rate of change and you can make it extremely small. So if I'm at this point, and let's say, actually I'm just gonna erase all of it and redraw a new graph. A bit higher. Let's say this point is the point at which we want to find our derivative. This x value is 3, and this y value is 8. So conventional knowledge would tell us here to here, boom, it would be 8 over 3. But that's not actually our speed right here. That's not our velocity. To get the real velocity, I'm going to demonstrate this. If I calculate from here as opposed to here, I'm going to get a different value. So let's say this is like 6, and this distance is like 2. So if I do 6 over 2, then I get a value of 3. But if I do 3 over, 8 over 3, I guess I'm more along the lines of like 2.5. So that's, you see how the rate of change is actually different. So depending on where the context starts, that's our speed. So like I said, we're going to go into the kind of the interesting detail theory of this. The way it actually started is Newton, Isaac Newton, was like, what if we just got closer and closer and closer and kept calculating the rate of change? Like, what if our change in y was like 0.000 something? And what if our change in x was like 0.000 something? Then what would our derivative be? Or what would our rate of change be? And that's how we get to our instantaneous. Hey.
Sorry about that.
Did y'all have the room reserved?
Yeah.
Okay, I'll move out.